Metamaterials are a revolutionary class of engineered materials that derive their extraordinary properties from their meticulously designed structures. These artificial materials are composed of periodic arrangements of sub-wavelength unit cells, smaller than the wavelength of the electromagnetic waves they interact with. This unique structural arrangement grants metamaterials the ability to manipulate light and sound in ways that defy conventional materials. By tailoring the geometry, size, and arrangement of their unit cells, scientists can control the electromagnetic properties of metamaterials. This control empowers metamaterials to achieve feats such as negative refraction, perfect lensing, and cloaking. From next-generation optical devices to advanced medical imaging, metamaterials hold immense promise for revolutionizing our world. As research advances, we can anticipate even more groundbreaking applications of these extraordinary materials. The concept of negative refraction, where light bends in the wrong direction, was long considered a theoretical curiosity. In the 1960s, Russian physicist Victor Veselago predicted that materials with negative permittivity and permeability would exhibit this phenomenon. It wasn't until the late 1990s that Sir John Pendry and his colleagues proposed that metamaterials could be engineered to exhibit negative refraction. In 2000, David Smith's research group successfully demonstrated negative refraction in the microwave region using a metamaterial composed of copper split-ring resonators and wires. This landmark achievement confirmed the ability of metamaterials to manipulate electromagnetic waves in unprecedented ways. The experimental verification of negative refraction ignited an explosion of research in the field, exploring applications from superlenses to cloaking devices. Electromagnetic metamaterials derive their unique properties from their ability to manipulate the electric and magnetic components of electromagnetic waves. Maxwell's equations describe the behavior of electric and magnetic fields. These equations relate to the material properties of permittivity and permeability. Metamaterials can tailor these parameters, even making them negative, by designing sub-wavelength structures. This control allows for manipulating light and other electromagnetic waves, leading to various applications. Metamaterials are classified based on the signs of their effective permittivity, epsilon, and permeability, mu. This classification system categorizes materials into four main groups: double positive, epsilon negative, mu negative, and double negative materials. Double positive materials are conventional materials found in nature, exhibiting positive values for both permittivity and permeability. Epsilon. Negative materials possess a negative permittivity, while their permeability remains positive, typically achieved using periodic structures of metallic wires. Mu negative materials exhibit a negative permeability while their permittivity remains positive, often realized using structures like split-ring resonators. Double negative materials possessing both negative permittivity and negative permeability are of particular interest due to their ability to exhibit phenomena like negative refraction. DNG metamaterials are typically fabricated by combining structures that exhibit negative permittivity and negative permeability. This classification system helps researchers understand the electromagnetic behavior of different metamaterials and their potential applications. For instance, DNG materials are being explored for creating perfect lenses and cloaking devices, while ENG and MNG materials have applications in antenna design and electromagnetic shielding. Near-zero refractive index metamaterials are engineered to have a refractive index close to zero. This unique property arises from the precise control over the effective permittivity and permeability of these materials. When light passes through a near-zero refractive index material, its wavelength becomes significantly elongated, effectively slowing down the phase velocity of light. This phenomenon leads to several fascinating applications, such as enhancing light-matter interactions. By confining light within these materials, researchers can significantly increase the interaction time between light and matter, leading to enhanced absorption, emission, and non-linear optical effects. This has profound implications for applications in areas such as solar energy harvesting, optical sensing, and non-linear optics. The unique optical properties of near-zero refractive index metamaterials make them a highly active area of research with the potential to revolutionize various fields. Metamaterials are categorized based on their dimensionality, which refers to the number of dimensions in which their structural periodicity extends. This classification distinguishes between one-dimensional, two-dimensional, and three-dimensional metamaterials, each offering unique advantages and potential applications. One-dimensional metamaterials exhibit periodicity along a single axis, often resembling a stack of layers with varying electromagnetic properties. They are relatively simpler to fabricate and analyze, making them suitable for applications such as frequency-selective surfaces and anti-reflection coatings. Two-dimensional metamaterials, also known as metasurfaces, possess periodicity along two dimensions, typically forming a planar surface with engineered electromagnetic properties. Metasurfaces offer greater design flexibility, enabling more sophisticated control over the polarization, phase, and amplitude of light, leading to applications in flat lenses, beam steering, and holography. Three-dimensional metamaterials exhibit periodicity along all three dimensions, forming a bulk material with complex unit cells, enabling the realization of exotic electromagnetic properties. The choice of dimensionality depends on the specific application and desired functionality, with three-dimensional metamaterials providing the ultimate flexibility in tailoring electromagnetic properties. Metamaterials hold immense promise for revolutionizing various technological domains. In telecommunications, metamaterial-based antennas and waveguides enhance signal transmission and reduce energy consumption. In medicine, metamaterials enable advanced imaging, diagnostics, and targeted drug delivery. Energy harvesting benefits from metamaterial-based solar cells and high-capacity batteries. Defense applications include cloaking devices and advanced sensors. The future of metamaterials is bright, with countless possibilities waiting to be unlocked.